there. So today what we're going to talk about are probability distributions and expected value. Okay, so what we're going to do is set up a whole bunch of different probability distribution tables, and we will talk about the way we go about setting them up, and then we'll compute something called expected value afterwards. Now, I claim with the probability distribution tables, we're really not doing anything different than what we've already done. What we're doing is we're organizing the information. Okay, so let me start out with an example here. Suppose you toss 2 coins. And what we want to do is note the number of heads that come up. And note the number of heads that appear. Now, when you are setting up these tables, you will always be told what it is you're looking for. So, note we want to find the number of heads that appear. So what we do is we set X to represent the number of heads that appear. You might recall these variables from an algebra class. This is really no different here. What we're doing essentially is we're saying, okay, we want to note the number of heads that appear. Since that's going to take on different values, just like in algebra, we set a letter to represent that. So in this case, if I am tossing 2 coins, I claim that the number of heads that can appear are 0, 1, or 2. So that's what your top row of your probability distribution table is going to look like. Now, what we put in the bottom row are the corresponding probabilities. Now, how you fill out these tables is dependent upon what sort of probability you're wanting to compute. You're going to see that sometimes we can list the sample space. Sometimes what we can do is use our combinations, and at other times a way we compute the various probabilities is using our binomial distributions. In this case, I claim we can list our sample space. Okay, if we toss 2 coins, one thing we could get are 2 heads. We could get a head and a tail. We could get a tail and a head. Or finally, we could get 2 tails. So let's talk about then how we would fill in our probabilities here. Well, what is the probability of getting no heads? Well, in how many places did we get no heads? That occurred once out of a total of 4 elements in our sample space. Recall the probability of an event is the number of ways it happens divided by the total number of possibilities. Okay, next, find the probability of getting 1 head. Well, that occurs in 2 places out of the 4. And finally, the probability of getting 2 heads, that occurs in 1 place out of the 4. Now, notice I didn't reduce my middle fraction. Yes, I would be very tempted to write that as 1/2. But one of the things that I'd like to point out to you is if you add up the probabilities in your probability distribution table, you should get 1. Okay? Now, if you have decimal approximations for things, you should get 1 within round-off error. So I take 1/4 plus 2/4 plus 1/4, and sure enough we get 4/4 or 1/2. So it's very good thing to note as a check mechanism that you add up your probabilities and you should get 1. Okay, so that's one example we have of a probability distribution table. Let's do another example. Okay, now suppose we have a bag and our bag contains 4 blue and 2 purple marbles. Okay, and what we do is we go in, we select 2 marbles at random, the number of purple marbles are counted. All right. Now, what we want to do is make another probability distribution table where we show the probability of drawing the various number of purple marbles that we can. So in this case, notice, we're counting the number of purple marbles. So, number of purple marbles. All right, so we ask ourselves, well, what values could X take on? Well, we could have 0 purple marbles, we could pick 1 purple marble, or we could pick 2 purple marbles. And no, not all of these tables have 0, 1, or 2 possibilities. Okay, now why do we max out at 2 purple marbles? For 2 reasons, actually. One of them is because we're only selecting 2 marbles. So even if we were counting the number of blue marbles selected, we would max out at 2. And the other reason why we max out at 2 here is because we only have 2 purple marbles in our bag. Okay? So, in this situation, this is one of classic scenarios where we use our combinations. Remember, whenever you have a collection of something and you're picking a sample of them, when the order in which you pick them does not matter, we use our combinations to compute the probabilities. So, in order to do these combinations, I first want to find out how many elements are in my sample space. Well, what's the total number of marbles in my bag? We've got 6 marbles, and we're choosing a sample of 2. So for each one of these, notice our denominator is 6, choose 2. Now what we need to do is figure out what our corresponding numerators are. Okay? Well, again, you have to account for your entire sample. Here we want no purple marbles. There's a total of 2 purple marbles in the bag, and in this scenario, we don't want any of them. But again, we're still picking 2 marbles. Well, if there's 2 purple in the bag and there's a total of 6, that means we have 4 blue, and we want 2 blue ones. In this case, again, for all of our numerators, the total number of purple marbles and blue marbles that we have to select from does not change. Just our sample that we're interested in changes. So here we want 1 purple marble. Since we're picking a total of 2 marbles, that means the other one is a blue. And here we want 2 purple marbles, and therefore no blue marbles. All right, if you compute these, you're going to get 6 over 15, 8 over 15, and finally 1 over 15. Okay, now it's fine if you'd prefer to put this in decimal form. I like to leave fraction form at times. Now, if I add these up, notice I get 15 over 15, which is exactly 1. All right, let's take another example similar to this. Okay, now what we're going to do is, instead of talking about marbles, we're going to talk about apples. So suppose I have a barrel of 25 apples. And in that barrel, 5 have worms. And then the rest are good. And suppose 3 apples are drawn at random. And what we want to do is count the number of wormed apples. All right. Well, let's do this table. Now what are we counting? We're counting the number of wormed apples. So let's ask ourselves, what values could X take on? Well, we could have no wormed apples, which is obviously our ideal situation. We could have 1 wormed apple. We could have 2 wormed apples. We could have 3 wormed apples, but notice I'm stopping here at 3. The reason why I'm stopping here at 3 is precisely because even though I have 5 wormed apples, we're only picking 3. So those are the 2 things that you need to look at in order to know when to stop making columns in your table. Okay, you have to pay attention to your sample size, and you also have to pay attention to however many things you're actually counting. Now, I claim this is another scenario where we're going to use our combinations. For each of these, I have a total of 25 apples, and I'm choosing 3. Now, in this first situation, imagine that, we want no wormed apples. Well, we have a total of 5 wormed apples. Okay? Now, if our barrel contains 25 apples and 5 of them have worms, that means that 20 of them, I'll say, are good. So for each numerator here, my top numbers are going to be 5 and 20, precisely because those are the total number that we have to select from. Okay? And again, my bottom numbers have to add up to my sample size. Okay? In this case, I want no wormed apples, therefore we have 3 good ones. Here I want 1 wormed apple, and therefore we'll have 2 good ones. Here I want 2 wormed apples. Well, if it has to add up to 3, that means I want 1 good one. And here I want 3 wormed apples, and therefore no good ones. All right, well, what you should get is 1,140 over 2,300. And again, you can put this in decimal form, whatever you're more comfortable with. Here you're going to get 950 over 2,300. Here you're going to get 200 over 2,300. And last but not least, you're going to get 10 over 2,300. Okay? So again, just to recap, with our probability distribution tables, what we're essentially looking at is we want to compute our probabilities of each possible scenario we're in, and we want them organized in a nice fashion so that we can look at them. Okay? And we can read off a lot of good information. Okay, so for example, one of the things that I'm going to read off here is, wow, it's really a lot more likely that we're not going to get any, and we're going to kind of max out at perhaps 1 wormed apple here. If you look at the probabilities, these probabilities are much higher than what we have over here. Now, the next thing that we're going to ask ourselves, and we're going to continue talking about these tables, but we're going to take this into a slightly different direction, okay? The next topic that we're going to talk about within this section is something called our expected value. In other words, how many, for example here, if we're in this situation, how many wormed apples would we expect to choose out? Now, what we're essentially looking at when we're talking about the expected value is the average or the mean, okay? Now, what we're going to do is we're going to first develop the formula using what we already know about how to compute the average or the mean, and then we'll take that and we'll figure out how we're going to compute such when we're given a probability distribution table, okay? So the way I'm going to start motivating this expected value is not the way that you're typically going to be solving these sorts of things, but I want to motivate the formula. I could just give you the formula right from the start, but I like to show you where it comes from and the meaning that it has. So what I want to do is what we're going to ask ourselves. We're going to say, okay, given a probability distribution table, how do we find the mean or the average? Okay, that mean or average is called our expected value. Okay, so again, you're not going to be doing it this way. What I'm doing here is I'm totally motivating where our formula comes from, given what we know about the mean. So, suppose you're in a class and you take 5 tests, and that's entirely how your course grade is determined. How do you find your class average? In other words, what your grade should be? Well, what you know to do is take all of your scores, in this case there's 5 of them, add them up, and then divide by 5. Okay? Keep that in mind because this is the sort of idea that we're using. Now, what I'm going to do here is as follows. Suppose I queried a bunch of families and I wanted to know the average number of hours of TV watched per day. Okay? And suppose I got this information, the number of hours, and what I'm going to have here is not a probability distribution table at the start. It's a frequency table. Okay? So, suppose this is my table. Suppose I have that 7 families, that's the frequency, said on average they don't watch any TV per day. Suppose 12 families report that on average they watch 1 hour of television per day. Suppose there's 4 families that say they watch 2 hours of TV per day. 3 families that watch 3 hours of TV per day, and 4 families that say they watch 4 hours of television per day. Now, could we figure out what the average number for all of these families combined is? We absolutely could. Okay, right? We have 0, 7 times, 1, 12 times, 2, 4 times, 3, 3 times, and 4, 4 times. So how would we do that? Well, yes, you could add 0 to itself 7 times, 1 to itself 12 times, etc. But we know that repeated addition is the same thing as multiplication. So to find the average amongst all of these families, well, we've got 0 times 7 plus 1 times 12 plus 2 times 4 plus 3 times 3 plus 4 times 4. Now, I need to divide by something. What do I divide by? I divide by the total number of families. Okay? Well, how many families are there? The biggest mistake people make is they think that they would divide by 5 since there were 5 columns here, but that's not the case. In order to figure out what to divide by, we have to divide by the total number of families. And if you add all those up, you get 30. Okay? So, before I go through and compute this, what I want to do is come on back over here to my probability distribution table. And what I want to do now is I want to show you how to go from a frequency table to a probability table. Okay? We're going to use the definition of probability. Remember, the probability of an event is the number of ways that event can happen divided by the total possible outcomes. Well, if I wanted to find the probability that one of these randomly selected families watched no hours of TV per day, well, in how many ways can that happen? Well, there's 7 families out of my total 30. Okay? How about the probability that they watch 1 hour of television per day? That's 12 families over 30. Again, what do? We just take the frequency, the number of ways it can happen, divided by the total number. Now notice, if you add up all of your probabilities, 19, 23, 26 plus 4 is 30. You get 30 over 30, which is 1. Okay? So, those are my probabilities. Now, let's go back over here. You'll see why I did that momentarily. But let's go back over here now, okay, and actually do some computations. Now, I will grant you that, number one, this is not how you're going to be computing them. All I'm doing right now is motivating the formula for this. But number 2, I understand that a lot of these steps are like seemingly going backwards from what you learned with fractions and common denominators and the like, but you'll see why I'm doing this momentarily. Okay? Notice I've got 5 terms in my numerator and 1 term in my denominator. Now, like I just said, typically what you do is you get a common denominator and put everybody over a common denominator. What I'm going to do right now is break this up into 5 separate fractions. Okay, I can certainly do this. Again, it might seem like I'm going backwards, but I assure you there's a reason. And now what I'm going to do is rewrite this in one other way. Okay, what I'm going to do is I'm going to write this as 0 times 7 over 30. Plus 1 times 12 over 30, plus 2, times 4 over 30, plus 3 times 3 over 30, plus 4 times 4 over 30. All I did is move my first number out in front, and we can certainly do that because, again, when you multiply 2 fractions, you multiply the numerators and you multiply the denominators. By default, we can say each of these have numbers in front have a denominator of 1. Okay? Now, if we actually even really cared what the answer is, we're going to get about 1.5 hours. Okay? But what I want you to do is notice that what I've written down here is equivalent to what I had over here, but now let's relate it to the table that we have. Notice, don't I have my first x value times its corresponding probability, plus my next x value times his corresponding probability, plus my next x value times his probability, and so on and so forth. Notice I'm taking each x value times its corresponding probability and I'm adding them up. And this gives us the way that we compute our expected value. Okay, the formula for expected value is as follows. E of x, you take your first x value times his corresponding probability. Then you take your next x value times his corresponding probability. And you go on down the line until you're done. Now, I'll write that out in English as well, in case that's helpful for you. It's a lot simpler to write it out in notation. But what you do is you take each x value times its corresponding probability and add them up. Okay? So what I would like to do now is just go through a few more examples, just to solidify. Okay? So suppose you were just given this table. Suppose we have the following probability distribution table. And let us say we have 4, 6, 8, and 10. And suppose the corresponding probabilities are 0.4, 0.4, 0.05, and 0.15. Now, the first thing that I'm going to point out is that this is a totally legitimate probability distribution table, because notice, if you take your probabilities and add them, you get 0.8, 0.85, and 85 and 15 is 100 or 1. Okay? So here we have a probability distribution table, and what we want to know is what is our expected value. Okay? Well, let's just look at our corresponding probabilities and get an idea in our head. I always like to do this because I like to confirm that what my intuition is telling me is actually what I finally compute. Okay? Notice the probability of 4 and 6 are very high. They're equal. And these probabilities are a lot lower. But they still exist. So what I would expect is that my probability is going to be between 4 and 6, but a lot closer to 6. Why? Because here I have a 20% chance of getting an 8 or a 10. Therefore, it's going to be pulling it in this direction. Now, what we can do is we can actually compute this to see what we get. You take your first x value times his probability, plus your next x value times his corresponding probability. So then plus 8 times 0.05 plus 10 times 0.15. And if you go through and do these computations, you're going to get 5.9, which is exactly what our intuition told us we would get. All right, let's do another example now. Okay, my next example is going to seem a little different, but we're going to walk ourselves through it. These are very, very common questions that you're going to come across when you have to make probability distribution tables, and these are called raffle questions. Okay, so let's go through and set this up. Suppose we were looking at a raffle, and suppose there was one first place prize, and suppose that person would win $400. Suppose there's 3 second place prizes, and those people would win $80 apiece. Okay? And suppose each raffle ticket costs $2, and 500 tickets are sold. What we want to do is find the expected payback for a person who buys one ticket. All right. Now this is a little different than what we've encountered, but we can certainly do this. Now, one reasonable question to ask is, how do you know what to do in a problem like this? Well, this again is very important where you pay attention to what you're reading. Notice you've got that keyword expected. So that tells us that we're going to want to compute our expected value. And we know that when we see it written like that, instead of average, we see expected value, what we can say to ourselves is, we need to make a probability distribution table. Okay? So, what we're going to let X represent is the payback for each person buying a ticket. Okay? Now, what I like to do is start out in the best case scenario. I claim the best case scenario is that we get the first prize and we win $400. But we got to pay attention because I claim we don't actually walk away with $400, right? We do win $400, but remember, we spent $2 on the ticket. So I claim what the first prize winner actually walks away with is $398. So they won $400, but we got to subtract off the $2 that they spent. All right, what's the next best case scenario? Well, you win second place. And again, yes, you win $80, but don't forget that you spent $2 for a ticket. So actually what you walk away with is $78. Now I'm just writing these numbers up here so you understand where these 78, and the 398 came from. Now, what about everybody else? Everybody else loses $2. Okay? So now let's go through and find our probabilities. Well, there's a total of 500 tickets that are sold. We'll ask ourselves, how many are first place winning tickets? There's 1. How many tickets win second prize? 3. And how many tickets lose? Well, everything else. So we have a total of 500 tickets. 3 plus 1, or 4 of them, are quote-unquote winners. So I claim that 496 of them are losers. Now, you're actually not losing anything because, as we all know, raffles generally are for a good cause. Okay? So what we have now is we have our probability distribution table set up. Now that we have that done, we can compute our expected value. Now, what do we expect to get? Notice the probability is so much higher right here. Okay, so we would expect to get a negative number. Yeah, 398 is a pretty big number. There is somebody who's going to be winning things. But most people are going to lose money, and therefore we can kind of expect that what's going to happen is that on average, people are going to be losing money. Okay, and this brings me back to something else that I want to say to you, is when you are taking the average, say, of those 5 tests that I alluded to before, very often when you compute your average, you don't get one of your exact test values. At times you do. More often than not, when you compute the average of a bunch of numbers, you get some funky decimal, okay? So, the same sort of thing as we saw with that last example of getting 5.9 also happens here. So you don't worry that you made a mistake if you get some funky decimal like, wait a minute, that's not possible. Nobody actually loses exactly that amount of money. Again, we're taking the average. So, to compute our expected value here, you take your first x value times his corresponding probability plus your next, so 78 times 3 over 500 minus 2 times 496 over 500. And if you compute this and round this to the nearest cent, you'll see that on average, there's a loss of 72 cents. And just like I stated, no, nobody actually loses 72 cents exactly here, but this is taking into account everybody. All right, so there's one last example that I would like to go through. So first what we're going to do is construct our table, and then what we're going to do is find the expected value. So suppose a family has 3 kids. And what we want to do is we want to count the number of girls. Okay? Now, I claim that we can actually construct this table using our binomial distribution. Let's remind ourselves why we can use a binomial distribution. Well, number 1, an experiment is repeated several times. Yeah, in this case, they're having 3 kids. Okay? Number 2, there's only 2 possible outcomes. Okay? So, in this situation, we're counting the number of girls, and the probability of having a girl is 1/2. And number 3, each trial is independent. Okay, this is a broad generalization, I will grant you that, but in general, this gender of one child is independent as to what the gender of your next child is going to be. Okay? So I claim that we can do this using our binomial distribution. So X is going to represent the number of girls. And let's actually construct our table. You're going to love this. This is cool. You'll see what this leads to. Okay? Well, what can X possibly be? They could have no girls, 1 girl, 2 girls, and 3 girls. We're assuming these are single births. Okay? Now, with each of them, what we can do is use our binomial, okay, to find the probability of exactly no girls. Remember, you use binomial PDF for each of these. And in this case, remember, you do your N. So we're having 3 kids. Probability of a girl is 1/2. And in this case, we want no girls. Here, it's binomial PDF again, 3 1/2, but now our X value is 1. Here, our X value is 2. And last but not least, binomial PDF, 3 1/2, and then 3. Now, if you do these computations, you're going to see that you're going to get 0.125, 0.375, 0.375, and 0.125. Make sure that you do get those values. Okay? All right. So now, what if I asked us to find the expected number of girls? Now this is a cool table. If we look at it, notice they're symmetric, right? One side of this table is a mirror image of the other side. So looking at this table, I see that these are weighted exactly the same. Therefore, I would expect 1.5. Again, you're not going to have a half a girl, but we're taking an average. So if we actually go through and compute this, you could take your first X value times his probability plus 1 times 0.375 plus 2 times 0.375 plus 3 times 0.125. And sure enough, if you do those computations, you'll see that you get 1.5. Super cool. But now I got to show you something, because this leads to something really cute, okay? So check this out. If we have a binomial situation, wouldn't we expect that 50% or half of the 3 kids are going to be girls? Yeah, we would expect that 1/2 of 3, okay? And sure enough, isn't 1/2 times 3 equal to 1.5? It sure is. So, really cool thing, going back to our binomial. And this is for a binomial scenario only. For your binomial only, your expected value is n times p. So you don't even have to make a distribution table if you recognize that it's a binomial distribution. Okay, so for example, and sorry, I know I said I was only going to do a couple more, but I've got to follow this up with just one more. Suppose it was found that 72% of people support candidate A. Okay, and let's suppose 225 people are surveyed. How many do you expect to support this candidate? Totally reasonable question to ask. Now, let's talk about this. First off, this is a classic binomial situation. Okay, again, an experiment is repeated multiple times. Yeah, we're asking 225 people. Two possible outcomes. Either they support the candidate or they do not support the candidate. And last but not least, presumably whether one person supports the candidate is independent as to whether the next person supports the candidate. Okay, so totally a binomial scenario. Now, let's talk about this. We see the word expect, so that indicates to us that we want to compute the expected value. There is no way you want to make a probability distribution table here. Okay, we'd have to have 226 columns in our probability distribution table. And my hope is that you're way too lazy to do something like that and that you've got much better things to do with your time. Right? Because we'd have to find the probability of exactly no people supporting the candidate. 1, 2, 3, 4, all the way up to 225. But we already know that it's about 72% who support the candidate. So wouldn't we expect that 72% of the 225 people support the candidate? And remember, of in math means multiply. So aren't we taking 72%, that's our p-value, times our n-value? So recognizing that, you just take your n times your p, and if you do this computation, we would expect about 162 people to support the candidate. Cool, huh? All right. Thank you.